Welcome everyone. I'm Maciej Bryński, and today I want to explain why Flink is all you need for a digital bank. But let me start with a short introduction. I have around 10 years of experience in big data domain with multiple contributions to many open source projects like Apache Flink, Apache Spark. Currently, I'm working as a data architect in Cledar, and I'm a former head of data at Digital Bank, so the project I will be talking today. Today I want to cover multiple topics, and I will start with business context. Then I will present solution design, and I will show our initial and final solution with their pros and cons. And at the end, I will explain how things are working on the examples. So let's start with business context. We are building new bank. This is new digital bank in Saudi Arabia. And as you probably know, banking is heavily regulated industry around the world. And Saudi Arabia is not exception here. Local regulator is called SAMA. It's Saudi Central Bank. And SAMA, as every regulator, has multiple requirements for banks. And reporting is one of them. But unusually, for so-called digital banks, some of the reports should be delivered in real time. And this includes multiple metrics, like number of customers or amount of deposit. So we built a bank architecture to deliver that. And this is very, very high-level view of the bank architecture. So on the left-hand side, you have our microservices. There are multiple of them. They have separate databases, storing entities like transactions, accounts, or customers. On the right-hand side, we have data warehouse, which is serving reports to multiple entities, including SAMA. And we choose data warehouse architecture as it's easiest to deploy, easiest to maintain, and it's good enough starting point for the bank. In the middle, there is a subject of this presentation, so this is real ETL data processing. Let's dive deeper. Bank is deployed on the Oracle Cloud infrastructure, and we're using MySQL databases for microservices. And as a data warehouse, we choose to use the MySQL HeatWave. HeatWave is basically MySQL on steroids, so it's super fast analytical database that is supporting MySQL protocol and MySQL dialect. And we choose to split our ETL processing into 3 separate parts. So we have extract, transform, and load, and we put Kafka as a messaging system in between. And this architecture has multiple pros. So first, we lower load on the microservices DB because there is only one process reading from them, and we are sure that all the data is ingested only once on Kafka. And this low-level architecture is also source of technical requirements for data processing technology. So we need to do multiple things here. We need to do change data capture from MySQL to Kafka. We need to have technology that is able to do real-time transformation and aggregation of data presented in Kafka. And at the end, we need to load data from Kafka to our data warehouse, so to MySQL HeatWave. On top of that, we want to be able to define as many parts of these pipelines in SQL as possible. And today, I don't want to explain in this presentation what CDC is, why we want to use CDC, because there's possibly dozens of presentations on this conference about this topic. And we evaluated multiple open source technologies that could be possibly cover our needs. This includes Kafka Connect, Debezium Server, Kafka Streams, Apache Spark, Apache Flink, and DBT. And as you can see from this table, Apache Flink was the only one that is covering all the requirements. And this was the main reason it was chosen for the project. But We also discussed different options. One of these was using Kafka Connect in conjunction with Apache Flink, but we have bad experience with Kafka Connect, especially regarding support if you are not enterprise Confluent customer. So we stay just with Apache Flink. But core Flink framework wasn't enough. So we needed one more library built on top of Apache Flink, and this library is called Flink CDC. So what Flink CDC is? It consists from two main modules. One is end-to-end data integration framework that can be used to set up real-time replication between two databases. And the second one is just a bunch of Flink CDC source connectors that has support for table SPI, SQL API, and data stream API. And of course, everything is built on top of Debezium, like probably every other open source CDC technology. Still multiple options here. So we have the CDC pipelines, we have SQL and data stream API, but problem with CDC pipeline is that it's not covering all our use case. So we needed MySQL source, sync, Kafka source, Kafka sync, and CDC pipelines doesn't have MySQL sync and Kafka source. So we choose to proceed either with SQL options or data stream options, and we used both in our solutions. Now I will present so-called initial solution. So we started with proof of concept that, okay, let's see if Flink CDC really can be used in our bank and if it's a solution for the bank needs. And if it can cover both use cases we have here, so which is real-time data replication and real-time data aggregation. And our initial solution was Flink SQL based. So every line of code was written in SQL, every line of transformation, ingestion, and extraction. And we just use generic SQL runners. So we have one Java process that is running any SQL code that was written. Everything is deployed via Flink operator on Kubernetes cluster, and we are doing some tests using test containers framework. So how this looks like deeper? Let's start with data replication. We have two Flink jobs here. One is data extraction from microservices DB to Kafka, and the second one load from Kafka to data warehouse. And to do that in Flink SQL, we need to define a bunch of tables. But let's start with some super simple model that will explain how things are working. So this is super simple customer model. Our customer has its ID, name, email, date of creation, and generally speaking, that's all. Of course, real-time, real-world data will be much more sophisticated, but for purposes of this presentation, this is good enough. And to do this data extraction process, we need two definitions of such tables. This one is a source, so this is using MySQL CDC connector, and it's reading from microservices DB. And this is destination. Destination is using Flink core Kafka connector. And to create data replication, you need only this. So this is one insert statement telling that we're reading data from MySQL and loading it to Kafka. And running this SQL in Flink will create super simple Flink job that is presented on the right. So you have one operator, that's all. And this is it. We have data extraction process to create tables, one insert. For load, it's even simpler because we can reuse Kafka definition from the extract job. And we need just to use JDBC connector to add JDBC sync to our data warehouse. Important thing here is that you need to specify all the column names we were using when creating tables. Sorry. And this is another insert. So this is road job. We are inserting data from Kafka to data warehouse. And on the right-hand side, you can see how this job looks like in Flink. And real-time transformation is also easy. So this is part of the data in our pipeline. So we're reading raw data from Kafka, and data is already there from the extract job. And the red lines are aggregation data path. And here we need to create aggregation table on Kafka using Kafka connector. And we need to have a data warehouse sync also. And final solution for aggregation is that we're using two SQL statements. One is aggregation. So you can see that we are casting timestamp as date and counting ID. And this gives us aggregation number of customers per date. And we're inserting data from Kafka to data warehouse. And this gives us jobs on the right. Sorry. So to sum up, we built our pipeline just with a bunch of SQL. We have 5 create tables, one in microservices DB, 2 Kafka topics, 2 in a data warehouse, and we create 4 Flink jobs. 1 extract, 1 transformation, and 2 load. And this is it. So we met all the bank requirements. And the question is, why not finish here? And there are multiple problems with this solution, and the main one is scalability. So this is a nice solution if we have only a few tables. But what if we have hundreds of microservices and hundreds of tables? So our replication pipelines needs 2 Flink jobs per every table. So we will have hundreds of Flink jobs. This is not the best way to replicate data, and it's very difficult to maintain. There are also other problems related to the Flink SQL. So we need to create data. We need to create tables in the data warehouse somehow. We need to introduce change management. And as you saw before, every SQL statement has included every column we were using. So adding column to source, new column in source needs to be added to every SQL statement. This is also difficult to maintain. There is no transactional support in Flink SQL JDBC sync. Of course, it can be overcome with absurd mechanism, statement in data warehouse, but it's not always the best solution. And the last but not least, setup of Flink SQL client can be tricky when you want to test your SQL statements. This is mainly due to dependency management in Flink SQL. So we need to change our solution, and this is how we prepared our final solution. So we choose to stay with aggregation part, as every aggregation has totally different SQL statements. And also, they are mainly using small subset of columns from source data, so changes to those queries occurs rarely. But for extract and load part, we need to move to something different, and this different is data stream API. So as a final solution, we created 1 extract job per physical instance of the database, 1 global load job, and with support for transactional JDBC sync. And for change management, we use multiple mechanisms. So first, we're storing JSON schema in Kafka with schema evolution. We also put all the JSON records to data warehouse, and then using views to extract data. And I will present this everything on the examples. So this is the result of switching to data stream API. So instead of SQL, we have a bunch of Java code. As you can see, it's kind of the similar. So you have the source, you have the sync. We were using MySQL CDC source from the Flink CDC pipeline, Kafka sync from the Flink core. And we need just to create pipeline from source to sink. So it looks easy, right? And almost. So there is tricky part in every Flink job, which is called serialization. And it looks like that. So when data is coming from MySQL CDC source, we need to deserialize this data and then serialize it back to send to Kafka. And this is totally different formats. This is how it looks like, how the object lifecycle looks like. So MySQL source beneath is using dbzoom, and dbzoom is using Kafka Connect structures. So we have Kafka Connect source record, and we cannot use it in the Flink pipeline because it's not serializable. So we need to deserialize source record into Java Pojo, use it in the pipeline, and then serialize it back to byte arrays that is part of the Kafka produce record, and it's sent back to Kafka. This is it. There is no tricky parts here, just few classes of Java code you need to create. For load, it's very similar. So we're using Kafka source, we're using JDBC sync, we're creating pipelines. Of course, you need to create this serialization schema, and then we encounter the final problem in this final solution, which is JDBC sync. So when you have JDBC sync, you need to pass insert or upsert statement as a part of creation of the JDBC sync, and you can only use one table here. So there is no way to parameterize this query by the table name, and we don't want to load data from all the Kafka topics into one table. So we create our own JDBC sync, and this is kind of the custom implementation only of one component of this JDBC sync, which is called statement executor. So in our solution, we need to create this custom statement executor and define few functions that it's used there. So first, this is key extractor, then statement creator, and parameter setter. And for every record, statement executor will first extract the key from the record. Based on this key, it will get or create prepared statement, and this statement then is cached in the statement cache. Then it's set all the parameters for prepared statement, add result to batch, and if the batch size is reached, then we just execute everything on the top of the data warehouse. And in our case, for key extractor, we are just using function that is getting topic name from the key. So then we can have separate prepared statement per topic, and this gives us possibility to send different topics to different tables. And to sum up, this is how our finalized solution looks like. So we have one extract job per physical instance of the microservices database, a bunch of Flink SQL transformation, one per every metric we need to create, one global job that is extracting data from Kafka to the data warehouse, and you can see the flow of the raw data and aggregated data on this diagram. So what are the problems in this final solution? Some of them are resolved, and I already mentioned that we create this JDBC sync for multiple tables. Some of them are resolved just on ourselves. So we had a compromise with microservices team that we'll be using JSON schema on Kafka as a format. So we needed to add JSON schema support to Flink as a separate format. We need to build change management, and we did it just thanks to JSON schema evolution, topic versioning, and using JSON columns in data warehouse with the views, and I will present it at the end. And one is still unresolved, so Flink CDC doesn't have support for new MySQL version, and by new I mean anything newer than 8.0. It's just not working, so this is the open bug. And let's finish with some examples. So this is extract job. On the left-hand side, we have customer database. So you can see the records, and on the right-hand side, this is how the record presentation looks like in Kafka. So this is a so-called division format, and you have some bunch of metadata, and at the top, the how the record looks like. So all the columns are there. This is aggregation. So this is our number of new customer per day aggregation, and it's working like that. So this is example. On the top, you have 2 Kafka records, and first one is just creating one new record in the aggregation topic, which is where the number of customers is 1. But the second one is working in a way which is called in Flink retract stream. So first, we're creating a record that is canceling previous one. So this is the second record on below, and the last record is record with the new value. And the load job, so we're just storing everything from Kafka straight to the database with whole JSON included. And at the end, we're using database views just to expose, to map fields from the JSON into something that can be consumed by some array and by any other data warehouse users. So this is it. Do you have any questions? Please.
Hi, thank you. We're also coming from a German bank, and we're interested, do you have any data lineage requirements? And if so, how do you face that?
Okay, I don't need my. So the question was, do we have any data lineage requirements? So the answer is yes, we have, and it's being built. So we use Open Lineage. There is a presentation of my colleague today about data lineage on Flink. So this is my colleague, so you can just go there and hear about how to use lineage from the Flink in the catalogs.
Thank you.
Hi, thank you for your presentation. What is the average end-to-end latency that you measured for this kind of replication?
It's currently okay. So it depends on one parameter, and this parameter is interval between Flink checkpoints, because we're using Kafka transactions, and as you probably know, transactions to Kafka are committed during checkpoints. So currently, we measure it below 1 minute, and for the summer requirements, it was enough. So real time was below 1 minute. So I would say it's near real time, but still it was good enough. So of course we can we may decrease amount of time between checkpointing, but it was kind of the good compromise between performance and the requirements that we had from regulator. So below 1 minute.
Thank you.
Okay, so thank you everyone for coming.